So here we are with our last module project, module 7, and we're going to do some optimizing with a quadratic objective. Um, and so I thought I'd just kind of go through some of these early parts because this can be definitely a bit confusing. So what we want to do is we want to retrieve this feasible region we had from project 5. So I've opened Desmos already, and again, all right, you go over here. Hopefully you've saved that project, and there's module 5. I open it, and so I opened it, and it says, okay, duplicate it, and give it a new name. And so if I just go up here and click on the name and say duplicate, now I've actually done this once already, so I'm going to leave this copy of name here on this. Normally I would delete that copy of part there. But anyway, I've got module 7, and so I'll save that, and so there I have this now as a project 7 graph. Okay, so what's happening this time? Well, again, we've got from both module 4 and 5, we've got those same budgetary constraints. We are using the module 5 equal to constraint for the number of counselors, so we're going to require 15 counselors. So in this case, we've set up a scenario where I've got 4 regions that, what's a region? Well, again, it could be a section of town, it could be a section of the county, it could be a county, it could be a state. It's kind of whatever it needs to be. But I've set up a system here where I put we'll say region 1 is an urban region, and region 4 is rural, and then you might guess that region 2 and 3 are somewhere between urban and rural. Maybe region 2 is some of the suburbs or something like that, and region 3 is beginning to get much more rural. It could even be very rural, just not part of region 4. And but just to make things simple and more intuitive as to how stuff might work, we've got the urban center here in the urban region, region 1. We've got the rural center that we're trying to staff and so forth here in region 4. And now we've decided that between the two centers we're going to have 15 counselors. But we don't know, how many for each center. What we want to do is the objective in this case is to minimize differences in accessibility to care. So just as you kind of look at this, it seems reasonable that people in region 1 and people in region 4 probably right off the bat seem to have more accessibility to the centers than regions 2 and 3, because the centers are in their regions. And so what we want to do is try to model that idea, but try to place our counselors so that the accessibility is the most even it can be between the 4 centers. And so we have some data. We have for each region, we have the demand for the centers. Now the demand we're just looking at what's one? Well, it's not saying it's one person. It's just a relative thing. So the Region 1, which is urban, has 6 times as much demand for counselors or counseling or the center as the rural center does. Okay, probably because there are more people. And regions 2 and 3, have 3 times more and 2 times more, respectively, than the rural center as far as demand. And then we can look at travel time, and again, we've got the time to the urban center. Well, maybe this is in minutes. That's probably what I was picturing when I did this. And so the average person in Region 1 needs about 20 minutes to get to the urban center, but they would need about 240 or about 4 hours on the average to get to the rural center. And then Region 2, about 50 minutes to get over here to urban center, about 70 minutes to get to the rural center. And then Region 3, about 75 minutes to get over here, and maybe 45 minutes to get over here to the rural center. Now, here's a case where you've got kind of a strange thing going on, is that, if you're in Region 1, it takes about 4 hours to get over here. But if you're in Region 4, it's saying on the average it only takes about 2 hours to get over here. So, whether things would be that disparate or that different, hard to say. But what I'm thinking of in terms of time is back at Module 1 and the different modes of transportation, and it could be, on the average, people over here in the urban center don't have as much, or near the urban center in Region 1, don't have access to automobiles, maybe. So they'd be looking at using the bus or, possibly some other type of transportation to get over here to Region 4 that might not be as fast as jumping in the car and driving over. Now, would it actually be twice as long? Who knows? As my grandfather always said, don't wreck a good story with facts. I just put some numbers in here to kind of get our attention and realize that, it may not be the same going both directions. And of course, with our story, a number of them would be probably pretty similar because in time, because it might be some sort of public safety transportation getting you from one to the other. But even that may change, so it could be that here in Region 4, if for some reason they need to get you over here to the urban center instead of the rural center, they put you in a sheriff's vehicle and drive right over, but maybe in the urban center, for whatever reason, they can't just use a sheriff or a police car. They have to use some other Department of Transportation kind of thing, and so it just may be slower. So we're just recognizing that it could be slower to go one direction than the other because of the demographics, because of access to transportation, that sort of thing. Okay, so there are the data we're going to work with. And now what we need to do is define this idea of accessibility. And we're actually using, now I didn't post the paper, it would be pretty tough to read. But it's, well, actually probably nearly impossible to read. But it's really based on some people who are looking at these questions And in here, they're, the title of their paper is Planning Toward Equal Accessibility to Services, and they say a quadratic programming approach. So in other words, they're going to use a quadratic objective function instead of linear. And they look at, I think, access to fire services, I think was one of them. And I know the other was to health services. So the health services is quite similar to our centers here, the crisis centers that we're looking at, because those are really a mental health kind of service. And so this just goes through some intuition as to how these people up here, Wang and Tang, define accessibility. And actually, they weren't the first to do it this way. They, in the paper, mention other people who have done this. And we're just trying to look at sort of how some of this is intuitive, is that access probably goes down as the distance to the center goes up. I think that makes sense, right? The farther away something is, the less you really feel you have access to it. If it's next door, that's easy to get to. If it's 200 miles away, that's not so easy to get to. It's not something you just do on a whim. And so that is like, some of the, a little bit of what we mentioned in Module 2. Now, we didn't actually do our project with inverse proportionality, but we've got kind of a proportionality thing going on here that access. Now, I just got a 1. I don't have a k for a constant proportionality, but it's proportional to 1 over the distance. Okay, so that means, as distance is smaller, this number is bigger. As distance is bigger, this number is smaller. So that's that inverse relationship. And so if we look back up here at the data, then we'd be saying 1 over 20 because we're going to use our travel time as our distance measure. Again, like Module 1. And so we've got 1 over 20 as an access there, and 1 over 240 is the access for Region 1 to get to the rural center. So 1 over that 240 and 1 over the 20. Okay. So that's the first thought. And then the second thought, as we're defining this, is that more counselors would also make something more accessible, right? Think about appointments, that sort of thing, is if you're trying to get in, whether it's an emergency situation or not, a follow-up kind of thing at the crisis center, maybe they do outpatient services at the crisis center. The more counselors you have on hand, the easier it will be to make an appointment or to get in during an emergency or something like that. And so that is a direct proportionality. And so we would have, access is equal to, again, there'd be a K, but something times the number of counselors. And so what we've got here then is we've put the number of counselors at the center in the numerator because it's directly proportional, but of course we've still got the inverse proportionality of the distance. So it's just saying, oh, maybe this is how we should define access, is take the number of counselors divided by the distance to the center. So again, if you look at the urban center for Region 1, you're still dividing by that 20. We're going to call it A11. Now, the first one is for the urban center. Since it's in Region 1, I thought I'd just use a 1 there. And then the second one is for Region 1. and we've got the number of urban councilors over that 20 minutes. But what's the number of urban councilors? Oh, remember we had X, so we defined the number of urban councilors as X, and Y as the number of rural councilors. And so we get this expression of X over 20. Now the problem is we don't know X yet, right? That's what we're going to optimize for, is to try to find that number of councilors. And then here, access to the rural center. Well, I used a 4 for the rural center because it was in Region 4, and then 1 because it's the Region 1 people trying to get there. And so we've got our rural councilors over the 240, the time to get there, Y over 240. Okay, so that's what that's doing. But number of councilors, so third, finally, the number of councilors doesn't tell you everything, because, say you've got 10 councilors at the urban center, but maybe you've got 100,000 people trying to use them, whereas maybe you only have 2 councilors at the rural center, but maybe you only have 1,000 people trying to use them. Well, so the demand matters as well, and the bigger the demand, again, the less accessible. Okay, so an inverse relationship, because as demand goes up, or maybe that's the population of the area or something, or related to the population, but as the demand goes up, you're going to have less access to that center because everybody else wants access too. Okay, so we end up with these sort of expressions for the accessibility to Center 1 for Region 1, and the accessibility to Center 4 from Region 1. Okay, now X and Y, those are variables we want to deal with, but this demand, what is it? What is that demand for the urban center? And so this next section just goes through defining what that would be. And so we've got this, it seems again reasonable that your total demand, okay, well, it's the demand for the center from Region 1, 2, 3, and 4. Well, except not exactly, right? Because, well, Region 3, well, they're likely to go to Region 4, and certainly Region 4 is likely to go to Region 4, but why? Because of that distance again. And so what those authors did was they defined the total demand as the demand, the total demand for a given center as the region demand divided by the distance to that center. Because again, if that distance is small, then pretty much all of that demand is going to go to that spot. But if that distance is big, so like from Region 4 to the urban center, then the demand is probably not going to be as big, even if this overall demand for Region 4 is pretty high. They're not going to travel all the way over here to Region 1 to go to that center. And so those authors use that inverse relationship with distance again and divide by that. And so our demand at the urban center, which I'll call D1, is the 6, because that was the Region 1 demand, but divided by 20 because it only takes 20 minutes to get there. Then 3 divided by 50, 2 divided by 75, 1 divided by 20, because again it took 2 hours for the Region 4 people to get to Region 1. So that's how we'll do the demand for the urban center, and the demand for the rural center, same idea. You see the demands on top are all the same, but the times are now reversed, sort of. Right, the biggest time here is under region 1 because we're now going to the rural center, and they took 4 hours to get there. So that's what this is doing, is defining what that is. And so if we take that D1 and D4 and we substitute them in here into equations 1 and 2, then we end up, so we're taking equations 3 and 4, substituting them into 1 and 2 respectively. And so our access to the urban center for region 1, this A11, is that x over 20 D1, but then that D1 was that number. And access to the rural center is whatever that turns out to be. Now again, I don't know x and y yet, so so we'll need those, but we'll need to use our feasible region and so forth to get that. Now, so our total access is just the access to the urban center plus the access to the rural center. And so we're going to say total access for region 1 here, A1, is the sum of those two separate accesses, and so we get this expression here that we'll call equation 5. Now, though, we have to do that same thing for urban and rural centers for region 2, urban and rural centers for region 3, urban and rural centers for region 4, and then add those together to get our total access for each of those regions. We're going to use decimals. Okay, so that is the definition stuff. Now what I think I'll do is go ahead and stop this video here and then make a second one starting with using decimals. So we'll stop this.